First of all, we are going through the history of development for mass-energy balance in open system. First, the ancient Greeks were the earliest to suggest that the quantity of matter in the universe remains constant. Nevertheless, the discovery of the law of conservation of mass is the most renowned for the work of Antoine Lavoisier. The law of the conservation of mass asserts that in a chemical reaction, the total mass of the products will consistently equal the total mass of the reactants. Next, Einstein revised this law in the form of the conservation of mass energy, which postulates that the total mass and energy within a system remain unchanged. These theories were subsequently expanded to assert that the quantity of atoms involved in a reaction remain constant in an open system. Now, let's take a look about the history of development for energy balance for open system. It starts from Sadi Carnot introduced the definition of work in 1824, which serves as the foundation of all contemporary thermodynamics. Then, James Joule experimentally determined the mechanical equivalent of heat and also laid the groundwork for the theory of conservation of energy in 1843. Rudolf Clausius further strengthened this thermodynamic law by debunking the caloric theories. Gibbs also formulated the first law of thermodynamics and introduced the concept of enthalpy, which plays a crucial role in open systems in 1876. He referred to enthalpy as the heat function at constant pressure. Other than that, Alfred Porter proposed the definition of H to be exclusively associated with enthalpy in 1922. These theories contributed to the development of the contemporary energy balance equation for open systems. Next, let's see the definition of mass balance and energy balance for an open system. First is mass balance for an open system. A mass balance for an open system is a fundamental concept in physics, engineering, and environmental science. It is a quantitative analysis of the flow of mass into and out of a system. In an open system, mass can enter or leave the system through inputs and outputs, such as material flowing into or out of a chemical reactor, a stream of water passing through a river system, or the movement of air in a ventilation system. Next is definition for energy balance for in an open system. An energy balance for an open system is a fundamental concept in thermodynamics and engineering. It involves the analysis of the energy inflows and outflows within a system, as well as the change in energy content within the system. Moreover, in an open system, energy can enter or leave the system through various forms of energy transfer, such as heat transfer, work done on or by the system, and the flow of energy carried by matter, e.g., a fluid stream in a pipe or a gas stream in a chemical reactor. Next, let's see the equation for mass balance and energy balance in open system. First, the equation for mass balance is delta mass system is equal to the mass system initial minus mass system final equal to mass in minus mass out. Next, this is the equation for energy balance for open system, which is delta H plus delta EC plus delta EP equals to Q minus work shaft. The following section discusses about mass and energy balance theories for open systems. Mass balancing for an open system, also known as material balance, is an application of mass conservation to the analysis of a physical system. The conservation of mass principle was used to form it. The same may be said for energy balance. It is analogous to mass balance because the energy of the system is conserved. It is generated by applying the law of conservation of energy, commonly known as the first law of thermodynamics. The law of conservation of energy holds that energy can neither be created nor destroyed. It is able to shift from one form to another. Here's an illustration to help you understand. If you were heating a pot of water on the stove, the system would consist of the stove, pot, and water, while the surroundings would consist of everything else. The rest of the kitchen, house, neighborhood, country, planet, galaxy, and universe. The choice of what to define as the system is arbitrary, up to the observer, and depending on what you want to examine, you could just as easily include only the water or the entire home in the system. The universe is made up of the system and its surroundings. Wind turbines are an example of an open system. Example of calculation. Question 1. Refrigerant 134A enters a compressor at 160 kilopascals as a saturated vapor with a flow rate of 0.35 meters 3 per minute and leaves at 500 kilopascals. The power supplied to the refrigerant during compression is 1.42 kilowatts. What is the temperature of R134A at the exit of the compressor? Let us show the solution to the example of calculation. First, let's define the formula of power. Power is equal to mass flow rate times with a change of enthalpy. Derive the formula to get enthalpy 2 as a subject. Next, mass flow rate is equal to volume flow rate divided by specific volume. Next step is, we have to look at the table for the value of specific volume and enthalpy at 160 kilopascals. This is the value of specific volume and enthalpy. By using MATLAB, we can calculate the value of mass flow rate and final enthalpy. Look at the formula of mass flow rate and insert the value of volume flow rate and specific volume. We can get the value of mass flow rate, which is 0.0472 kilograms per second. Next, calculate the value of final enthalpy by inserting the value of initial enthalpy, power and mass flow rate. The value of power is negative because work is coming in. The value of final enthalpy is 271.2184 kilograms per second. The final temperature is calculated by using interpolating. By referring to the table, from the value of final enthalpy that we have calculated, 271.2184 kilojoules per kilogram is located between 267.73 and 276.27, which is between 50 and 60 degrees Celsius. Therefore, we interpolate to get the final temperature. The answer is 54.0185 degrees Celsius.